What is up, amigos? Today we're going through the effects of wing flaps on performance, and there are a bunch of different flaps we'll go through, and we'll go through the theory of them as well. So why do we want these wing flaps to begin with? Well, let's say we have a regular wing, we have a cross-section cutting straight through. So this is the cross-section here. And this can be, let's say, a NACA 0020 airfoil, which if you don't understand this terminology, check out this video in the card here. And let's say it's going at an angle of attack of 10 degrees. So the flow goes over and we produce a bunch of lifts. So we have the angle of attack down here, and we have the lift coefficient here, and let's say 10 degrees is here, and we have a lift coefficient of about 1 being produced. This is quite standard. Now, the problem is that as we go higher in the angle of attack, we often lose lift and then we get stall. And often we actually want to get a lot more lift than what we are getting for particular applications. For example, if we have an airplane taking off, a lift coefficient of 1 is not going to cut it. We want to get to 1.5, 2, even higher. So to do that, we have these things called wing flaps, and we have a bunch of different ones. So we have ones called trailing edge wing flap, or trailing edges effectively. So we have the exact same wing, let's say, and at the back, we have now this flap that comes down. And we can actually change this angle of attack independently from this airfoil here. So what this does is, it does a couple things. One, we have the center line of the airfoil, and we can actually look at the camber. So by changing this flap here, we effectively increase the camber of this airfoil. Now, if you don't know what camber does, check out this video here. But effectively, it increases the slope of this curve. So let's say we have this curve originally. If we introduce camber to the wing, legitimately or artificially with this flap, we move this line up. So we actually now have this going on. And by increasing this flap angle more, we increase the camber of the wing even more. A second thing that we can do is by spacing the trailing flap from the rest of the airfoil, we can actually get this flow coming here, and it shoots through this part here and goes over this flap bit. Now, why we want that to happen? Is this beneficial? Well, the answer is yes. And the reason why is because we have the flow coming over the airfoil to begin with. And as it goes over the airfoil, it loses energy the more it goes. And it gets to a point where it really wants to separate, so the flow wants to actually lift off. Now, if we can introduce some faster moving flow at some point downstream, what we do is we re-energize the boundary layer. That's the technical term for it. What we do is we just effectively introduce higher velocity near the wall that then shoots the flow more down this way and keeps it attached more, which means we can actually push this airfoil to a higher angle of attack and not get stall. So we'll actually start to get stall maybe around here, which is 20 degrees instead of the 15 or instead of the 12, let's say, that we're getting here. So that's how trailing edge flaps work. And we also have other ones called Kruger flaps, leading edge slats, and leading edge droop. And they all are quite similar in terms of the principles of how they work. Let's go through these ones as well. So again, we have the airfoil. I'm going to draw it without the trailing edge flap. And what we have here is at the front, we can have, let's do the Kruger flap first. We have a part of the wing that actually, from the here about, down on the pressure side, it will actually start to come out. So if we extend it, it will actually look like this, if I can draw it properly. So why would we want this flap? This is called a Kruger flap, by the way. The flap comes from underneath and flings out. Well, there are a couple of things that we want to consider first. First of all, we want to look at how this extends the airfoil effectively. To begin with, we had let's say a symmetrical airfoil, so no camber. But now if we were to draw a center line between the leading edge and the trailing edge, we can now see that there is, and then the center line, we can now see there is some camber. What that does is, again, it moves this lift coefficient line up, and that means that this airfoil is producing more lift at any given angle of attack. Another thing that we can do, we don't necessarily have to do it, but we can do it, is again, create a separation between this Kruger flap and the rest of the airfoil. So air can actually come through here and again, re-energize the boundary layer and keep the flow attached even longer. Again, that's not necessarily the case, but we can do it if we want to. What about leading edge slats? Very similar to Kruger flaps, except instead of having this flap down here, we now have the airfoil, and we have a flap that actually extends forward from here. So again, we now get this extension here. So for leading edge slats, it's not very common for us to increase the camber of the wing by extending this. We often put it at an angle where it doesn't really affect the camber very much, but we can do it if we want to. We can extend it further down this way more aggressively or less aggressively, whatever we want. Usually leading edge slats, what we do is we actually create a separation point between the slat itself and the rest of the airfoil, which we then can shoot this air through, as I mentioned here, and keep the flow attached at a high angle attack so we can push the airfoil higher and get more lift. That's the main operation of the leading edge slat. Again, we can always extend it further down and increase the camber, but that's not necessarily the case. Finally, leading edge droop. This is probably the most radical idea of the entire series that we've covered here. What we actually do is we get this entire front section and then we rotate it entirely down, so we get something that looks like this. So this entire section has now moved down. And what this does is, as you can see, it increases the camber of the airfoil. And that again increases this lift curve slope here. We often don't have a gap between the leading edge section and the rest of the airfoil, which means we don't get this increase in the still angle attack, but it can be done if we really want to. So that is how the different types of flaps of a wing work and the principles behind them. If you like this video, make sure to like it. If you want to see more like this, click the subscribe button. And if you want to learn more about these flaps, check out a book by John D. Anderson called Fundamentals of Aerodynamics. You can find it in the link in the description. And if you want to learn more about aerodynamic theory and or CFD, check out our courses that we put on as well. We go through things like this, but in a lot more detail as well. And you can find them in the link in the description as well. And I'll see you. Peace amigos.